Hi folks, today we're looping back for some more optimization. We're going to do some questions that involve shortest distance and also a little bit on financial or business stuff. But before we get to some optimization questions on shortest distance, let's investigate the distance between 2 points in a plane. So here I have a point A and B, and I'm wondering what is the distance between them. And maybe the easiest way to figure out that distance would be to make a little right triangle. Now, the sides of this would have one leg that is the change in x between A and B, and the other leg would be the change in y between A and B. And this would give us the distance. So from Pythagorean theorem, it would be fair to say that the square of the distance is just the sum of the squares of the legs of that triangle. Now, since we're actually interested in the distance, not d squared, let's square root both sides. And the distance is going to be a positive quantity, so we don't have to worry about the plus or minus. There's a nice equation for the distance between any 2 points. Sometimes people like to make it a little bit more explicit. So one thing we can do here is say at point A we have coordinates x1, y1, and point B we have coordinates x2, y2. And that means the change in x, well, it's usually final minus initial anyways. So it's going to be x2 minus x1. There's change in x, and we square it, plus change in y, so that would be y2 minus y1. There's another nice equation for the distance between 2 points. Now that we have a distance formula, let's put it to use in a question that asks about shortest distance between a line and a point. So we want to find the shortest distance between the line y equals x plus 3 and the point 4, 2. Step 1, draw. So 4, 2 would be right here. There's my point. And the line y equals x plus 3 has a slope of 1 and a y-intercept of 3. I'm just going to make a rough sketch here. Looks something like that. And you can see if you're on this line, your distance to this point varies. It's quite far away if you're over here. And if you're, say, over here, your distance is now shorter. Okay? There's some shortest point, let's call it xy, on this line. And it minimizes the distance between the point and the line. There's step 1. We've defined our variables. They were already just going to be x and y. So now we're ready to make an equation. And the thing we want to optimize is distance. And we have a distance formula right here, so let's use it. We're going to want to label these ones x1 and y1. I like to do that with the point. You can do it either way. And then this general point here is going to be our x2, y2. Those are unknown. All right, so the equation that we want to optimize is for distance. It's x2 minus x1, so that would be x minus 4, all squared, plus y, that's my y2, minus y1, all squared. We could expand this if we want, but right at this point we can see that there's trouble. There are too many letters, so let's see if there's something in the question that helps us re-express one variable in terms of another. And it's actually right in the definition of that line. Every point y on this line is actually just x value plus 3. So that gives us a little substitution we can make. So I've got x minus 4 all squared. Where I see y over here, I can put in x plus 3. And then minus 2 all squared. I can clean that up a little bit. So I have x minus 4 all squared. Plus, let's see, this will be x plus 1 all squared. And now I have a nice equation in terms of a single variable. Now I'm going to have to differentiate next. I'd prefer to expand these out. You can do it either way, but you have to be wary of the chain rule. So I'm going to expand those binomials. X minus 4 times x minus 4 gives us x squared minus 8x plus 16. If you need to do that off to the side, that's fine. X plus 1 all squared gives us x squared plus 2x plus 1. Collect our like terms, and we have the square root of 2x squared minus 8x plus 2x makes minus 6x, and then plus 17. There's a really nice equation for the distance between this point and this line. Our next step is to differentiate, so before I do that, I may want to rewrite this with an exponent, or you may know some tricks for differentiating square roots, and that's fine. So notice this is still d. I haven't differentiated yet. Now I'm ready to differentiate. This is a function with an outer part of a half, power of a half, and an inner of that trinomial. So when I differentiate, I have to deal with the half. It comes down front. Nothing happens to the inner part yet. Power goes down to negative 1/2, and now times the derivative of the inner, which would be 4x minus 6. Now I can put those together in maybe a slightly prettier form because it looks like a big old mess. So if I write this as one fraction, this 2 belongs on the bottom. This whole trinomial is a square root on the bottom, minus 6x plus 17, and then this 4x minus 6 goes on the top. If you wanted to, you could factor this out and reduce it. It doesn't help us a whole lot, so I'm not going to bother to do it, but absolutely that's an option. Great, so we've differentiated, and now we've got to find the critical value, which looks like it's going to be a big mess. I'm going to take a second and just clean up a little. I'm ready to hunt my critical values, so I just sub in 0 for d prime. That's equal to 4x minus 6 all over 2 root of this big old mess. That looks like a difficult equation, but remember, you can just multiply both sides by this denominator, and you'll get 0 on this side, and you'll be left with just 4x minus 6 on the other side. And we continue to solve. We get 6 equals 4x, or x is 3 over 2, or we could call it 1.5. Now we know that's our critical value. It either makes distance as small as possible or as big as possible. We can tell from the sketch that it's going to make it as small as possible, and it does look like a reasonable point for us on the sketch where x is 1.5, but we should confirm that we actually have a minimum. So now that we have this critical value, let's go and do a test. If I do the first derivative test, I can put in something smaller than 1.5 into the first derivative, so I could put in, say, 0. I'll get negative 6 over this bottom, and that bottom's always going to be positive because of the square root. So I'll get a negative in total. If I put in, say, 2, then the numerator will be positive and the whole thing will be positive. We've gone from decrease to increase. Oh my, we have a min at x equals 1.5. Now normally we'd also say we could use the second derivative, and you can in this case, but look at the kind of mess we've got on the first derivative. Finding the second derivative is not going to be pleasant at all. So you could do it, but let's not. Lastly, let's actually answer the question. What is the shortest distance between the line y equals x plus 3 and the point 4,2? There's actually a nice expression around here that gives us that distance just in terms of x. So I'm going to plug into that. At x equals 1.5, if we put it in, we get d equals 2 by 1.5 squared minus 6 by 1.5 plus 17. or the square root of 12.5. And we can go to our calculator and approximate that. I get that the minimum distance is about 3.54 units. And to find that, I didn't need to find the y value. There's the distance that is the minimum. If I really did want to go back and find the y value, well, I guess now we know that x is supposed to be 1.5 at this minimum, and y is just x plus 3, so y is 4.5. But that's not what the question's asking. Here's another minimum distance question, but if you understood the last one, feel free to press pause and just do this, skip ahead and check your answers. Otherwise, follow along. So we're wondering what coordinates on the curve y equals root x plus 4 are closest to the point 3, 0. Let's draw it. Here's 3, 0. The curve root x plus 4 is a square root graph that starts back here, left 4. It doesn't ever go down. There we go. So there's some point over here that is closest to this point 3, 0. Let's call it xy. There's our drawing. I don't know if it's perfect, but it gives us an idea of what's happening. The distance between these points comes from the distance formula. And we want to know what these coordinates are. So here's my x1, y1. I'm going to call this x2, y2 to use in the distance formula. So I'd have x2, which is my general x, minus 3 all squared, plus y2, which is my general y, minus 0 all squared. Right away, we can see there's a problem here. We've got too many letters, but we can use this fact to sub in. Every y coordinate here is just root x plus 4. Some people are going to want to just start with that, and that's fine. They're going to start with this step I'm about to write right here. Root x plus 4 minus 0 all squared. All I did was sub in for y, and I put in this. Now I'm going to do a little bit of expansion just to make it look a little nicer. So x minus 3 all squared is x squared minus 6x plus 9. Root x plus 4 minus 0 is just root x plus 4. If you square it, you'll just get x plus 4. Squaring something with a square root undoes the square root. Putting together our terms, we're going to have x squared minus 5x plus 13. That's a lovely expression for the distance, and that's the thing that we want to minimize. I'm going to rewrite it with the power of a half, just because I'm going to differentiate. But there are some tricks you can use. I'll put them up in the corner over here. You can click on a video that has some tricks that help you differentiate square roots of functions. All right, here we go. Half comes down, nothing happens to the inside. Power goes down by 1 times the derivative of the inside, which is 2x minus 5. Looks like a complete mess, so let's write it in fractional form. So this 2 lives on the bottom. We have square root of x squared minus 5x plus 13 on the bottom as well. And this 2x minus 5 on top. And some people are just going to see the critical value at that point. If that's the case, great. Write it down as soon as you see it. Otherwise, we hunt our critical values by setting the derivative equal to 0. 2 root of x squared minus 5x plus 13. And just times both sides by this bottom. And if you noticed that earlier on, then you can just go straight to this little equation. 5 equals 2x, or x is 2.5, which looks like a reasonable x coordinate over here for our minimum distance. There's our critical. Geometrically, I think we know that's a min, but we want to prove it, so we'll use the first derivative test for a max or min. If I put in something less than 2.5 into the first derivative, say I put in 0, I'm going to get a negative. If I put in, say, 3, I'm going to get a positive. So distance is going from decreasing to increasing. That means we have a min at x equals 2.5. Great, we've done most of the hard work. Now we just have to make sure we answer the question. So the question is, what are the coordinates? So now I know this is 2.5 for x. What's the y coordinate going to be? Well, it's going to be whatever you get when you sub in 2.5 for x. So it'll be 2.5 plus 4, or the square root of 6.5. Those are the exact coordinates. Let's write them over here. Distance is minimized at these coordinates, or you can get them in decimal approximation. That's about 2.5 and 2.55-ish. Show it either way. So the steps are still draw, make an equation, fix the equation, hunt your critical values, and test for a max or min. We'll do one other question that involves a different type of application. Here's our last optimization example, and this one involves money! So the cost of producing X t-shirts is given by this contrived polynomial over here, and then t-shirts are sold for 15 bucks each. And what you might be interested in is, how do I make sure that I make the most money that's possible? And as soon as you say those words, the most, then we know that it's an optimization question. We want an ideal situation. Generally, profit is revenue minus cost, so it's money that comes in minus money that goes out. And our first question is to write an equation for revenue. So revenue is the money that comes in. Let's think about it. If we sell one t-shirt, then $15 comes in. If we sell 2 t-shirts, then it's $30. If you sell 100 t-shirts, then it's 100 times $15 each. If you sell X t-shirts, it's going to be 15 times X. So revenue is going to be 15X. Write an equation for profit. So profit is the revenue, the money in, minus the money out. So revenue, we already knew, is 15x, minus, here comes cost, and here comes one of the most common errors as well. Did we really just subtract off the cost function? Nuh-uh. We only subtracted off the first term of it. To subtract it all off, put it in brackets. Let's simplify a little bit. Okay, so we have negative 0.01x squared, we have 12x, and we have negative 1,000, meaning that if you sold 0 t-shirts, you would have a profit of negative $1,000, or you'd be in the hole $1,000. Now to find the max on this, we could use 521b stuff, grade 11 stuff, but let's keep going with our calculus techniques. So we'd go for part C. How many t-shirts should be produced to maximize profits? Let's find P prime, because we're hunting down a maximum. Let's find our critical value, so set P prime equal to 0. And then just solve. I can take my calculator and divide by 0.02, or I could think multiply both sides by 100, then you'll get 2x equals 1200, and divide by 2. Either way, we'll get x is 600. That's our critical value. Now again, we know from grade 11 stuff that this right here is a parabola that opens downward. That means this is guaranteed to give us a max. Let's use calculus techniques just to make sure. Option 1 is to use the first derivative. If I put in, say, 500 into P prime, I'm going to end up with a positive number. Or if I put in 1 into it, I'm going to end up with a positive. If I put in 1,000, I'm going to end up with a negative number. In other words, P goes from increasing to decreasing. So profit has a max at x equals 600. In this one, we could also have done the second derivative test for a max or min. So the second derivative here is negative 0.02, which is always negative, so we're always concave down, which means we have a max at that critical value. So we've established that there's a max at x equals 600. Let's make sure that we answer the question. How many t-shirts should be produced to maximize profit? X means the number of t-shirts. We've actually answered the question here. If we wanted the profit itself, we'd plug it into one of these P equations. But our answer is 600 t-shirts should be produced. Now at this point we've done optimization questions that involved construction, that involved shortest distance, and that involved a little bit of economics or financial stuff. But really optimization has to do with any question where you're looking for a max or a min. So there are a bajillion other types out there, but this is where we're going to cap it in terms of our investigation right now. Good luck with the practice, and let me know if you have questions.